You probably think of a computer as a screen and a keyboard, but if we look closely at a modern home, we find hidden computers running the spinning washing machine, checking the smart thermostat on the wall, and even stabilizing a drone lifting off outside. These don't look like the classic, bulky desktop machines. They don't have operating systems with millions of files, app stores, or overlapping windows. These are embedded systems. An embedded system is a specialized computer built directly into a larger piece of equipment, designed to do exactly one job continuously. This isn't a new concept. If we look at this specialized keypad and green digital readout, we are looking at the Apollo flight computer that helped land astronauts on the moon. It was hardwired for spaceflight calculations and absolutely nothing else. You can't use an embedded system to browse the web or play a video game. They are specialized brains engineered specifically to bridge the gap between digital code and the physical machines we rely on every day. To see how these systems are structured under the hood, let's look at a familiar piece of hardware, a standard smart thermostat. If we peel back the physical casing, we find the printed circuit board. This flat surface holds the fundamental organs of the device, divided into 4 main zones. Right in the center is the microcontroller unit, or MCU. This is the brain that acts as the central processor for the entire system. Next to it is the memory block. This stores both the permanent instructions written by the engineers and the temporary data the system needs while running. Then we have the inputs. Think of these as the senses. They capture raw data from the real world, like the current room temperature, and feed it to the brain. Finally, we have the outputs. These are the muscles. They take the brain's digital decisions and translate them back into physical actions, like displaying a number on a screen or clicking a heater on. Whether it is a cheap children's toy or a multi-million-dollar jet engine, every single embedded system in existence is just a scaled variation of this exact same arrangement: a brain, memory, senses, and muscles. This diagram shows the continuous loop of logic that an embedded system runs thousands of times every second. I like to call this the digital reflex. Here is how that reflex plays out in real time. First, a sensor detects a physical change in the environment, like rising heat, and converts it into a digital signal that the brain can read. Next is the processing step. The microcontroller compares this incoming data against the strict rules stored in its memory to make an immediate, logical decision. In the final step, the microcontroller sends a voltage command out to an actuator to perform a physical correction, like turning on a cooling fan. Because this loop operates without the distractions of a full desktop operating system, it provides ultra-reliable millisecond precision. That predictability is why we trust these systems with critical tasks, like deploying anti-lock brakes or regulating medical pacemakers. Because physical tasks vary wildly in complexity, engineers must carefully choose the right microcontroller architecture for each specific job. For simple tasks like reading a button press, engineers use a low-cost 8-bit chip. Think of the 8-bit part as the size of the chip's notepad. It can only handle small, simple lists of information at once, which is perfect for basic learning. But an industrial robot needs a 32-bit processor. If the 8-bit chip is a small notepad, this 32-bit architecture is like a massive multi-lane highway for data, allowing the brain to calculate complex movements instantly. Sometimes the main requirement is getting the device online. In those cases, engineers reach for chips like the ESP32, which feature Wi-Fi and Bluetooth antennas built directly into the hardware, so the device can talk to your phone. This chart shows how processor speed relates to power consumption across different chips. If a device runs on a small battery, a high-speed chip will drain it fast. Instead, an engineer will choose an ultra-low power chip like the MSP430, which can run periodic sensor checks for years on a single coin battery. Selecting a microcontroller is never about finding one best chip. Instead, it is a careful balancing act between processing power, battery constraints, and the physical demands of the project. Now that we understand the hardware, we have to ask, how does a human actually write the instructions that command the physical world? To do this, developers rely on foundational programming languages like embedded C and C++. These languages allow them to communicate with the hardware and directly manipulate the chip's memory. Different chips on a circuit board also need a way to talk to each other. They use specialized protocols that work like a high-speed metronome. This clock pulse keeps both chips in perfect sync so they can correctly read the rapid flashes of electrical ones and zeros passing between them. On advanced hardware handling dozens of tasks simultaneously, developers use a real-time operating system. Think of this as an air traffic controller that ensures every signal arrives at exactly the right millisecond, preventing any data collisions. Writing the code is only half the job. Engineers must also understand basic electronics, because a software bug in these systems is high stakes. A single line of wrong code can physically overheat and destroy the circuitry. Mastering this specific blend of software coding and electrical engineering gives a developer the power to dictate exactly how the physical and digital worlds interact. Because of that strict level of control, there is a massive demand for embedded systems engineering in industries ranging from electric vehicles to aerospace and factory automation. This expertise is the core of modern roles like firmware engineering, IoT development, or robotics architecture. As the Internet of Things expands, the traditional dividing line between mechanical engineering and software development is disappearing entirely. You can start exploring this field today. Take up a basic development board, write a simple script to blink an LED, and take your first step into making hardware respond to your commands. Embedded systems are the reason our world responds to us. By understanding this simple loop of input and output, you are looking at the logic that will drive the next generation of technology.